All right, so we're gonna get started on the second lecture on chapter 10, and this is actually a continuation of section 10.1. In the previous lecture, we introduced a family of substitution cryptosystem known as mono-alphabetic cryptosystems. And we found out that in these cryptosystems, they are easy to actually attack. They are vulnerable to decryption, either because we could use the exhaustive key search when the key space is small in size, such as in the case of Caesar spheres or in the case of affine spheres. And on other types of these crypto systems, such as the permutation sphere, we could use statistical frequency analysis to attack these type of spheres. So one way, of course, to avoid this or to go around this weakness of these types of spheres is either by increasing the key space, and unfortunately, but because of the nature where each letter is actually kind of encrypted to the same letter in the sphere text, we could use a statistical analysis. So the next step is to try to scramble the frequencies and not always associate or use the same letter, the plain text or clear text letters. We associate with them different letters, not the same letter throughout the message. So this way we defeat the using the frequency analysis. Now, with this frequency scrambling is accomplished by, again, removing this this component, which we call the non-alphabetic restriction, that every occurrence of a letter in the plain text message be in spheres constantly by the same sphere text. This leads us to the following type of substitution spheres called polyalphabetic substitution sphere. And in this case, the correspondence between the characters that appears in the plain text and those appearing in the sphere text is not one-to-one. So in other words, each letter may actually be encrypted as different letters. So we don't know that is the frequency, it's gonna actually vary, so we cannot use the frequency analysis anymore. The most famous example of a polyalphabetic sphere was published by the French cryptographer. Actually, his profession, he's a diplomat, and his name is Blaise de Vigenère. He lived between the years 1523 and 1596. And the crypto system he created, we refer to it as Vigenère spheres. The key of the Vigenère sphere consists of a keyword. So we choose a keyword, all right, say of a given length, n, which consists of these alphabets or these letters, L1, L2, up to Ln, and I'm going to assume these are letters in the English language. And suppose that the numerical equivalent of these letters are K1 up to Kn. Now, to encrypt a plain text message, first we split the message into blocks of length n, which is the same as the key. So a block consisting of letters, let's say one block, or with a numerical equivalent using, again, the letter A, 0, 0, the letter B, 0, 1, and so on, and the letter Z is 25. So let's say we take a block of a message and the numerical equivalent to the character or the alphabet in the on this block, B1, P2, up to Pn. Then the idea is to add or do addition mod 26 of P1 to the K1, that is the first numerical equivalent of the key, and then we add P2 to K2. So in general, we're going to come up with the sphere text whose alphabets or whose numerical equivalent is this sequence, C1 up to Cn, where C sub I is adding P sub I to K sub I mod 26. And then, of course, adjust the C sub I's to be between 0 and 25. So in this case, the Eigenray spheres maps blocks of plain text letters, which the same as numbers, of a fixed length n, which is the length of this keyword, to blocks of sphere text or letters or numbers of the same length. Now, we could choose if the terminal block of a message has fewer than n letters, we could add some dummy letters to make it of the same length, or we just actually truncate it and don't use the last block could be actually shorter. And with this also, we're going to make the key that will be also with a shorter length. So the idea is just to keep adding basically for each block in the message the key, okay? So this way, with the letters, they are not gonna appear over and over again, okay? Because it depends on when you are adding a given letter, the A might appear at the beginning, so you're gonna add K1 to it, and later on in the message it might appear on the third place in another block, and you're gonna add to it K3 and so on. So the frequency here, it's going to be lost. To formally describe the Eigenray sphere, it's going to be like this. First, we're going to take n to be a positive integer. That's the length of the block, or the length actually of the key. And we take the plain text and the sphere text as well as the key space to be Z26 n, means just the sequences or a product, Cartesian product of Z26 by itself n times. Then we choose a key. Again, this stands for a common, not common word. Actually, it could be any type of word. And then we define the encryption on a sequence of numbers of length n to be adding x1 to k1, x2 to k2, and we do the addition of each of these components mod 26. Now, the decryption is going to be basically the same. We're using the same key, except this time we're going to do subtraction mod 26. Here's an example. So let's assume that we take n, the length of the keyword, to be 6. And let's assume the keyword is sphere. And this keyword corresponds to the numerical value 0, 2, 0, 8. Just write them like this. And then suppose the plain text message is this. This crypto system is not secure. So first we're going to convert this crypto system is not secure to blocks of length 6 this time, and then which is going to be this CR, Y, crypto, and so on. And then we're going to add the keyword to each of these blocks, which is sphere, sphere, sphere. And we do this one, of course, using numerical value for the letters. They are associated with the letters and the keyword. We're going to have it actually like this. So these are the letters or the numerical values of the message divided into or partitioned into blocks of length 6. So the first 6 is here, and then we have the key underneath. Then we just do add 19 to 2 mod 26, we get 21, and 7 to 8, 15. And then we go to the second block, which is the next 6 letters or their numerical values, and we add the key again. And then we repeat this, and the red colored actually numbers, it stands for the sphere text or the numerical value of the sphere text. The last block, it turns out to be shorter than 6. It only has length 3. Again, we could add some a letter XXX, for example, or something like that. And then we use the whole key, or we just could truncate it like I did in here. And so when we convert these numerical values into the letters they actually represent, then we come with this is the sphere text message. As you see, it doesn't make any sense, of course. To decrypt, we use the same key, except we're going to subtract from each one of the sphere text the key over and over again. So for example, if I look at the to decrypt the first block, which was 21, 15, 23 from the sphere text, 25, 6, and 8, we just subtract 2, 8, 15, and we get the first block. Now, for this system, first of all, we know that the frequencies are mixed up. Means they are scrambled. We cannot use a crypto analysis for it, or it's going to be a little harder at least. The other thing is the key space for this crypto system is quite large, because we could use any keyword, let's say of length m. So, and all possible keywords, they're gonna actually, there is a total of 26 to the power of m. So even when m is relatively small, then exhaustive key search would be actually require a long time. Even for m is equal to 5, we're gonna find that the key space actually is more than 1.1 multiplied by 10 to the 7, which is, you know, by hand, this is very hard to try all these keys. However, it turns out that this one is actually not a secure system, but it's much better than, you know, the mono substitution crypto system that we introduced earlier. Here is a modification of the Vigen-Ray sphere. It's called Vigen-Ray auto key sphere. This modification makes actually make it much harder to break, and that's the idea about you know, modifying a crypto system. So in here, instead of repeating the keyword over and over in order to encrypt a message, the keyword is only used once. In fact, the idea is to start off with a keyword that is short. In fact, it just consists of one letter. We refer to it as a seed or primer. And we put it at the beginning of the plain text, and then we truncate from the plain text the letters of the same length. So if I put in a seed that has 3 letters, for example, then we truncate it from the end of the plain text 3 letters. All right? But in general, I said we usually use a single letter. So we put a single letter and then we remove a single letter from the end of the plain text. Just remove it. So let's see how this actually does work. And then we just actually add the message to the original message to the altered message by putting the seed in the front. So let's assume that the message is very simple in here, the word hello. And let's assume that we use as a seed the letter N. So here we go, hello. It corresponds to the numerical values 7, 4, 11, 11, and 14. Now the word, we're going to put N in the front and then remove the O at the end. And we put the numerical equivalent to these letters. And then we add the original message, hello, to the modified message with the keyword added. And then we do the addition mod 26. So we come up with these numbers, 20, 11, 15, 22, 25, and in letters, they correspond to these, again, meaningless, this meaningless word, basically. And so this is the sphere text. Now to decrypt, we just do subtraction mod 26. Again, if we have more than one block, we could use the same seed, or we could actually use different seeds for different blocks, actually, to make it harder to break. And of course, the seed here must be shared by the 2 parties that they're going to actually correspond with this private communication. All right, another type of crypto system is called the Hell sphere. And this is another example of a polyalphabetic crypto system. This crypto system was invented in 1929 by Lester Hell, and it is defined this way. So we're going to start with M being a positive integer. And we're going to define the plain text space and the sphere text space to be Z26M, means, again, the Cartesian product. And the idea is to take, actually, for encryption, a linear combination of the M alphabetic character in one plain text block, or sometimes we call it element. All right, a linear combination means multiples of these numerical values of these characters in a block of the message by just different numbers. And we're going to see there are some restriction on these multiples. And producing, of course, M alphabetic characters, and that's going to serve as the sphere text block. So let's look at an example. This is very actually simple. Suppose we take M, means blocks of length 2. And we could write a plain text consisting of 2 letters or 2 numerical values for these letters, x1 and x2, and the corresponding sphere text element or block as y1 and y2. Now, y1 and y2, they're going to be given as linear combination of x1, x2, and again, everything is done mod 26. So, for example, we could take y1 to be 11, x1 plus 3x2. So this is just an example of linear combination of x1 and x2, and y2 to be 8, x1 plus 7x2. It's like a system sort of equations or congruence equations in here. Now, we can, as you know, write this system of congruences using the matrix notation. So this is y1, y2 is the sphere text or sphere equivalent, the numerical equivalent of a text, two letters. And then we have the matrix that consists of the coefficients of the congruence relations. Then x1, x2, and this is just regular matrix multiplication. Of course, in order for this system to be able to decrypt, we're going to use sort of the mechanism of linear algebra, and that is by multiplying by the inverse of this matrix. So here all the operation again are performed mod 26. Here's an example where how we're going to do the decryption. So K, and then we're going to find the inverse, and we're going to find the inverse mod 26. And as you see, one good thing about this, it's not going to have any fractions. All it's going to be whole numbers, because the numbers is going to be from actually up to 25. So this is 27 in here. Actually, it should be just 1. All right. So this should be actually 1 in it. So if I take for example, the plain text to be the word July, then we divide this into 2 blocks because we're using m equal 2. And we call them x1, x2, x1 prime, x2 prime. And then we encrypt the x1, x2, which is 9, 20, by multiplying it by the matrix 11, 8, 3, 7. And we get 3, 4. And this corresponds to the letters O, E. Similarly, we go with LY, which corresponds to 11, 24, and this gives me the sphere text correspond to x1 prime, x2 prime to be L double. So here is the sphere text, and to decrypt, we just multiply by the K inverse. I am sorry, it looks like the K inverse is supposed to be 23. So there is a mistake in here. This one is 23, it's not the 27 actually. So here it is. If we want to define the sphere hill formally, again, we take, we divide the message into blocks of length m, where m is bigger than or equal to 2. And our sphere, our plain text space and the sphere text space is the Cartesian product of the 26 with itself m times. And the key in here are going to be m by m invertible matrices over Z26. And then the encryption for a key, which is going to be a matrix on a vector, a column vector X is going to be just the product of K to the left by X, and the decryption we multiply by the inverse. So in order so the key space must consist of these invertible matrices. Here is another crypto system. Actually, it goes back to 1917. And this crypto system actually has what is called perfect secrecy. And it's referred to as Verman one-time pad. As the name indicates, means that the key that we're going to be using, it only can be used only once. And from a practical point of view, of course, this is not practical, all right, because you have to exchange keys, regularly, and it turns out this is really not a very useful one. However, it's very, very hard to break. That's why we call it its perfect secrecy. And this was actually discovered by Gilbert Verman in 1917. And to describe this, we're going to take n to be a positive integer. And the Verman one-time pad encrypts actually bit strings, means strings which of course translate from letters to zeros and ones of length n. The plain text space and the sphere text space and the key space are all actually strings of bit strings, or we sometimes call them binary strings. So the set 0, 1, n means the product of 0, 1 by itself n times. It's the Cartesian product. And the encryption function is we take a key, which consists again of a string of zeros and 1, and we associate with a string of zeros and 1. This is the plain text string P of length n by adding P to this string K, or again of zeros and 1. And the addition is done component-wise mod 2. Okay, so we do binary actually addition. So if P consists of this string P1 up to Pn, zeros and ones, and K1 up to Kn, then we just add each of these components, and we either get a 0 or a 1. And here is the way, these are defined. If we take P sub I, K sub I to be all possible combination of zeros and ones for these is going to be like this. So 0 plus 0 is 0. And as you see, 1 plus 1 here is going to be, of course, equal to 0. And the decryption, we just do the same thing. We add actually, because each element here it's kind of its own inverse mod 2. So if we have a sphere text C, which is equal P plus K, so if you add a K to this, then K plus K is going to actually give you 0. The string which consists all of zeros, and so we recover the actually the plain text P. Here's an example. So let's take n equal 5, and in this case we're going to be using the bit representation of the alphabet from A to Z. That's given in the textbook on page 202, and this is referred to as Burton codes. It's discovered by a French mathematician. I think it's a mathematician. And so each letter actually, it's coded with binary code of length 5. Okay, that consists of 5 digits of zeros and 1. So this is an example actually is taken from the textbook. The message that we want to encrypt is act now. So if we write the binary string equivalent to act now, of course with no spaces in between, so it's going to consist of these strings length 5, 5, 5 that give us the act now. And then if we take the key to be, again, this strength of zeros and one, and when we add them, we come up with this is the sphere text. If I add, it's not very hard to see, the key again to the sphere text, then we actually recover the act now, or the plain text. And then we cannot use this key anymore, okay? So it'll be very hard for anyone to determine actually from intercepting the sphere text at the end in here to find the original plain text. All right, so far, the crypto systems that we discussed in one form or another uses actually modular arithmetic, means either addition, modular addition, or modular multiplication. In the 1970s, mathematicians looked at using exponentiation, modular exponentiation, and came up with a family of spheres called exponentiation spheres. And the first type of exponentiation sphere was introduced or invented in 1978 by Pauling and Hellman. And we can describe it like this. We're going to take a P to be a prime, odd prime. Usually it's going to be a large odd prime. For our purposes and examples, we're going to take of course, not a very large one, but a shorter one. And we're going to let E, the encryption key, to be actually a randomly selected integer with the property that it is relatively prime to P minus 1. Now, to encrypt a message, we first translate, of course, the letter of the message into a numerical equivalence using, again, the regular A00, B01, and Z25. Next, we partition the string of numbers that actually give us the message into blocks of 2m decimal digits. Remember that each letter, it consists of 2 digits. So we want the blocks to be actually has an even length, where 2m is the largest positive even integer such that all blocks of a numerical equivalent corresponding to m letters are less than this prime P. So for each plain text block, let's call it capital P, which is an integer with 2m decimal digits, we form sphere text by calculating the P, okay, that's the block. Again, this is a numerical, it's going to be a number, to the power of E, mod the prime P. And then, of course, we're going to always have the C between 0 and to less than P. So the sphere text message, again, is going to consist of these sphere text blocks, which are integers less than P. Now, to calculate this block P to the E, we use what's called fast exponentiation. And when we look at an example, we're going to see what that is. Because as you know, raising a number to a power, and E usually it's going to be a large also exponent, it might take some time, but it turns out there is an algorithm that we could use that make this easier. Because we're going to be doing raising to different exponent and then reducing the the result mod the prime P. All right, here's an example. Suppose we take the prime to be 2633, and we take a key, the exponentiation key, to be 29. And it's not hard to see that actually E and P minus 1, their greatest common divisor is equal to 1. And let's assume that the plain text message is this. This is an example of an exponentiation sphere. So the first thing we want is to choose an M. And this time we're going to take the M, which is blocks of length 4. Means it's basically two letters for each block. And then we have the message in here, all translated into digits. The very last one is actually 23. This is an extra digit added, which represent the letter X, just to make this one actually all the blocks has the same length of 4. Now we're going to calculate in here each block in here. We're going to raise it to the exponent of 29. And as I said, this is very hard to do even with a calculator if you were to just plug it in. Instead, what we do is we start with this P. Let's say we take the 1907, the first block, all right? And then we square it. Then we reduce mod 2633, the prime P. And then we get what we call this number square. And then we take the square of that. So it gives me this number to the power 4. And then we reduce mod 2633. And then we go with 2 to the 8th, which means the square of the previous one, and so on. And then what we do is basically we're gonna be then kind of multiplying these all together to come up with the 429, okay, which is actually is gonna be this number to the power of 4, and then to the power of power of 16. Which is the 2 to the power 4, plus this number to the power of 8, which is 2 to the 3rd, and so on. So in other words, we're going to use what is called the binary representation of the number, and actually using the square of each one of these. And then we obtain, of course, the sphere text message, which is this. As you can see, by no means, this is something you wanted to do by hand for a long time. I mean, it's very time consuming, even with the use of a calculator. But all these crypto systems, the one that appears in the 1970s, actually they have a computer or the use of computers in mind. So this is one of the earlier, advances sort of in cryptography using exponentiation sphere. So to decrypt actually a sphere text message or block C, we need to know or find what we call a decryption key. And this one, we take it as an integer D that is the multiplicative inverse actually of E mod P minus 1. And we know such a number exists because E and P minus 1 are relatively prime. So then E does have a multiplicative inverse. And we can find the multiplicative inverse using the Euclidean algorithm. All right. And so here it is. Now, why we gonna get the original message when we take C and raise it to the D exponent? Because remember, C is equal to, or it's congruent to, P to the power of E. So when you raise this this is C, and when you raise this to the D, we get P to the power ED. And now from the congruence, DE is congruent to 1 mod P minus 1. We convert this into a divisibility relation. So we can write it as K, that's DE, is equal K times P minus 1 plus 1 for some K. And then we split this into a product of P to the power P minus 1 to the K, and then we remove the plus 1 in here as P. But because of Fermat's theorem, P to the power P minus 1 is congruent to 1 mod P. All right, and then what we recover is P itself. All right, and here is actually an example of in other words, the decryption key for the previous example is 2269. And if you use this key to decrypt the first block in the sphere text, you get back the original one. And you have to do this one, of course, for every block. Again, this is a very long and lengthy process to do, even with a calculator. All right. I'm going to pause for a minute in here, and then I'm going to start introducing another family of crypto system. Is called public key crypto system. All right. So it's going to. All right, so we're going to continue with introducing what is called public key crypto system. So far, all the crypto systems that we discussed, actually, they are examples of what is called the private key systems or symmetric crypto systems. Because the encryption key and decryption key must be exchanged between the two people that are going to communicate, or knowing an encryption key, it's easy to obtain a decryption key from the knowledge of the encryption key. So if we wanted to use this kind of crypto system to establish communication within a network, then and to keep the communication private, so each two persons in this network must actually exchange these keys, and it's going to be kept again secret from the other in the network. And this is of course to be not a convenient way. So the thinking back in the 1970s start. Can we establish a crypto system that actually a person publish sort of the encryption key for others to use to encrypt or send this person a messages, and then the person would receive the message can actually use his own private secret key to decrypt the message. And if it is intercepted by others, then they will not be able to actually understand. So these type of crypto systems are called public key crypto system. So they're characterized by having the encryption key known, and actually the encryption function, means the way the encryption is done, is also known. Only thing which is secret is the decryption key. So this new type of encryption system are called public key crypto system, and was invented again back in the 1970s. All right, so in here we're gonna discuss one of the most important crypto system that is referred to as the RSA public crypto system, which is still actually in use today. And this crypto system was invented in 1978 by 3 computer science mathematicians, referred to the name of Ronald Rivest, Adi Shamir, and Leonard Adlerman. And this is based again on modular exponentiation, where the key consists of a pair of numbers, n and e. And the n is going to be actually the modulus that we're going to use in the exponentiation, and e actually is the exponent. And n itself is going to be the product of 2 large primes. And we talk about 2 large primes are primes which has 200 digits or more. And also there's a criterion in the selection of these primes using some random prime generator to generate such primes, not to choose primes of a special form. So n is going to be a product of 2 primes. Let's call them p and q. And e, we want it to be, which is the exponent, to be a number that is relatively prime, again chosen randomly, that to be relatively prime to the phi of n, where phi of n is the Euler phi function evaluated at n. Now, to encrypt a message, we first translate the letters into their numerical equivalents. And then we form blocks of largest possible size, 2m, and we want 2m to be smaller than the n. And later on, we're going to see what is, to be known and what is not known. Basically, n will be known, but not the prime factors of n to be really, revealed. In other words, these going to be kept secret. So to encrypt a plain text block p, we do an exponentiation, all right, or we compute c, which is going to be this block p to the power e, using again fast exponentiation, which is repeated squaring and then reducing mod n. Now, the decryption procedure, and it's going to require the knowledge of an inverse d of e mod phi of n. And which we know it again exists because the greatest common divisor of e and phi of n is equal to 1. So the decryption key is going to be an inverse of e. And this is going to be, of course, kept private. And to decrypt the message, simply we're going to take c to the d. Now the question is, and we're going to do, of course, this exponentiation model. Now, here's the important question. How can you be sure that when the recipient decrypts the plain text, he or she gets the original plain text? We're going to answer this question by a theorem, which states this: if M, or if we let M be a message or a block in a message, with M being smaller in size than N, but M is going to be a number, where N we know it is equal PQ, but of course it's not revealed, with P and Q are distinct large primes. And we're going to let the encryption key, which is known publicly, it's like published in a directory, like a telephone directory or something like that. And the decryption key is D, which is again private. So let's assume we have a sphere text C, which is obtained by encrypting the message M, like raising it to the power A, and doing a mod N computation. And let's assume M prime is the decryption of C using the key D. Then this theorem is saying we're going to find out that M prime is going to be actually M. To see why this is the case, so let's just start with M prime being the exponentiation of the sphere text C to the D. And if I put back what C is, it's ME all to the D mod N. And of course, we will be done if we can show that the result of this double exponentiation is going to give me actually back M. So then we get M prime is equal to. Well, let's see here. First, we show that actually MED is congruent to M mod P, which is one of the prime factors of N, where E and, you remember that E and D are inverses of each other, mod Phi of N. So which means when we take their product, it's going to be congruent to 1 mod Phi of N. So if I turn this congruence relation into equality, then we have ED is going to basically equal 1 plus Phi of N for some T in Z. And I could write Phi of N to be P minus 1 times Q minus 1. Remember that P and Q are distinct primes, and these are, in general, are large primes. There are two cases to consider. One case is M and P are not relatively prime, which is equivalent to saying that P is a factor of M. So in this case, M is going to be congruent to 0 mod P. And then we can raise both sides of this congruence to the exponent ED, and we get 0. So then we have, by transitivity, M is congruent to 0, M to the power ED is congruent to 0, so M and M to the power ED is congruent to each other mod P. Then the other case where M and P are relatively prime. And in this case, we can apply Euler's theorem so that we have M to the power Phi of P is congruent to 1 mod P. And then if I substitute for ED by what it's equal to in terms of the prime factors of N, or the Phi of N, this is what we get. We just do some basic algebraic manipulation in here, and we get actually to use either Fermat's theorem or Euler's theorem to get this M to the power Phi of P is congruent to 1, and then we get this is congruent to mod P. So we have shown that M to the power ED is going to be congruent to mod P. Similarly, we can use the same argument to show this is also true for Q. So together, then we have These two congruences give us P divides M to the power ED minus M, and the Q divides the same. Then, since these are distinct primes, relatively prime, then their product divides the M to the power ED minus M, which means they're going to be congruent to each other mod PQ, which is equal to it. So yes, we recover the original message M by doing encryption followed by decryption using the keys E and D. The other important question is the security of this system. It's based on what? So in other words, we know that E, the public key, is known. We know N is known. Now, is it true that knowing E and N, it's going to be very hard for someone to find the D, the private secret key D? Well, it turns out that if someone actually can factor N, find P and the Q, then they can find phi of N, and then they can find an inverse of E mod phi of N. And then they would have the, actually the secret key, it will be revealed this way. So now we're going to see that, so the key here is either even being able to factor a large integer, or if someone somehow can obtain phi of N from E and N. And it turns out actually it's the same thing. It's going to be as hard as factor. So if you think about it, this means that the security of the RSA depends on the inability to, to have an algorithm that can factor large integers. And in fact, there is no known algorithm that in general can factor large integers, let's say with 400 digits in a reasonable amount of time. So here it is. Now we're going to see that the RSA cryptosystem is as secure as the factorability of N. So far, no factoring algorithm is actually yet discovered, and that is effective. Next, we're going to find that to show that finding phi of N, which is actually the key, if we know the factoring of N, and it's finding P and the Q is not easier than factoring N. It means it's the same difficulty of obtaining the value of, Euler's phi on N. We know that if we know the factor, then we know what phi of N is. But assume we don't know the factors, then is there another way we can actually find phi of N without knowing its factor? Below, we're going to see it will be really the same. So first, remember that phi of N is going to be equal P minus 1 times Q minus 1, assuming that we know P and the Q, okay? Then we can express, of course, phi of N in terms of N and the prime factors of here. And then we can write P plus Q as N by just solving for P plus Q in here. That is N minus phi of N plus 1. And we can also use that little trick in here to write P minus Q as the square root of P plus Q quantity square minus 4 PQ, or this is the same as P plus Q square minus 4N. Also, it's not hard to see that P is nothing but 1/2 the sum of P and the Q plus P minus Q. Q cancel out and you get 2P, you get P. And also Q, we can write it in terms of P plus Q and P minus Q. And these P plus Q and P minus Q are written in terms of actually N and Phi of N. Again, assuming that we know N and we wanted to find Phi of N from that and E. Well, consequently, as you can see, P and Q can easily be found when N and Phi of N are known. Okay, so if I know N and Phi of N, then we can find P and Q from this set of equations. And of course, it's the same thing, means either factoring or we need to know Phi of N. So there is no other alternative to be able to find the P and the Q. Here is an example of how the RSA actually crypto system works. This is an example from the textbook, example 10.4. And in here, we are using for P and Q, 37 and 73. This is very, very small primes. And it gives us an N of 2701, and we are taking E to be 47. Again, that's a number that's relatively prime to the phi of this, 2701. All right, and if the message is no way today, first we're going to translate this into numerical values, and we then partition this into blocks of a given length less than n, and here we'll partition it into blocks of length 4. And then we take each block and we're going to compute this block to the exponent e, which is 4.47. And then we, after translating or finding the exponentiation of each block to the 47 and reducing mod 2701, we find the plain text. And then we find a key, the decryption key, to be the multiplicative inverse of E, which is 47 mod phi of n. And again, we use the Euclidean algorithm to do this. And then when you do the decryption, you're going to find out, yes, it will give you back the first plain text block. There is one other issue that actually these public crypto system they have. They provide what is called a digital signature. For example, when you send an email to a certain person, they know that this email is coming from you, and you cannot deny that this is an email from your sort of an account. And this is done by actually using this crypto system that supply what we call a digital signature. So here it is, and the question becomes here, when we receive an electronic message, how do we know that it has come from the supposed sender of the message? So to do this, we need what is called a digital signature that can tell us that the message must have originated with the party who supposedly sent this message. So this is called authentication of the message. And for example, this is done when you do electronic mail or electronic banking and many other situations where this is important. Now, in here, we're going to see how the RSA crypto system actually achieved this. So let's assume we have two individuals individual I and individual J. And individual I wishes to send a signed message to J. And we're going to assume that, of course, he has the public key, which is E sub I, and his private secret decryption key, which is D sub I. The same thing for the individual J, has a public key, E sub J, and the secret key, it is D sub J. So we're going to be using this. So, and I is going to be sending a signed message to J. So this is what I is going to do first. It's going to actually take a plain text block, P, all right, and is going to use his private decryption key and calculate P to the D sub I, mod Ni. Now remember, Ni is known. That is the product of two primes for the encryption and, of course, decryption for individual I. And the encrypted message, we're going to denote it by this S. Okay. Then, if the encrypting key for individual I, which only individual I we know that knows the D sub I. Now then, individual I is going to look and see if the N sub J, that is the number that's associated with the other person, which is known, again, is bigger than Ni, where the E sub J, again, N sub J, is the encryption key for individual J. Individual I encrypts S by using the public encrypting key for individual J. And so it's going to raise this S, this block S, into the E sub J mod NJ, just a regular kind of encryption. However, if N sub J is smaller than Ni, he's going to split the this message S into blocks so that they are smaller than N sub J, and they're going to encrypt each one of these blocks using the same kind of procedure. Just raise it to the E sub J. So let's assume that S is in fact, the length of it is or the N sub. The N sub J is actually bigger than N sub I. So we can do it for this block. All right. Now, individual J is going to receive this message, which is C, which is individual I encrypted using S, which was encrypted, decrypted sort of, by applying D sub I. And this is what this person is going to do. So they're going to use their private key to apply it to C. And then what do they get? They get actually S, all right? Because the encrypted sort of the sphere text message they receive is S. And then when they, it's encrypted and then decrypted. Now to find the plain text message, P, the original one, individual J is going to actually use the public encrypting function or key of individual I and apply it to S. But remember that S is going to be the decryption of key sub I on P, and this gives you the P sub to the power of D sub I to the E sub I. But this one, because d sub I, e sub I is congruent to 1, mod n sub I, so this is going to give you at the very end, actually, the P. And again, the reasoning for this is because d sub I, e sub I is congruent to 1 mod phi of n sub I. By doing just the simple calculations, you're going to find actually it gives you P mod n sub I. So the combination of the plain text plot and P and the signed version S convince individual J that the message actually came from I. Also, individual I cannot deny sending the message because no one other than this individual know the message or the signed message S in order to actually the original message was converted into S, and nobody can do that. Mean convert P to S because using it's secret. And here it is. So we have a full system of communication, which is, as I said, it's actually used, and it has the advantage of not just the messages are exchanged, privately, but also it can be known that this is a legitimate authentication of these messages. And if you again think about it, this system is based on the failure of mathematics actually to solve factoring problems. So because the security of this it depends on the inability to factor the n, because if we know how to factor n, then we can find the decryption and this system becomes definitely not secure. All right. So far, no factoring methods actually is available to factor a large integer in a reasonable amount of time, even with computers. All right. So there are two more sections I'm just going to be covering, and they are much shorter actually than this section. So I'm just going to stop right here.